Revealing the hidden truths. Child malnutrition through an isotopic lens. Childhood obesity and undernutrition are global health problems, but isotopic techniques are now providing highly accurate tools for understanding malnutrition and its consequences. Globally, 15 million children under 5 are stunted due to poor nutrition in utero and in early childhood. Nearly 51 million children under 5 suffer from wasting due to poor nutrient intake or disease. At the same time, 38 million children under the age of 5 are overweight because of poor diet and physical inactivity. These and other forms of malnutrition are common among lower socio-economic groups all over the world, particularly in Africa and Asia. Isotopic techniques are helping researchers around the world to better understand multiple forms of malnutrition. They provide a more accurate measure of body fat than the commonly used body mass index or BMI. So just what are isotopes and how can they help measure all forms of malnutrition? Isotopes are variations of the same element that have different weights. This difference means they can be used as tracers to measure body composition and understand biological processes. For example, deuterium is a heavier isotope of hydrogen that can be used to measure the amount of water in the body. Two isotope techniques are useful in the study of childhood malnutrition. The deuterium dilution or heavy water technique accurately measures body composition by determining fat-free mass and fat mass. The doubly labeled water technique can help determine the amount of energy a person uses each day. Why is this important? Monitoring body composition is important because changes to overall fat and fat-free mass are associated with the risk of diet-related disease. Total energy expenditure can be used to determine a person's physical activity level and give an estimate of energy requirements. Here's how the techniques work. Body composition. A person drinks a specific amount of deuterium oxide, also known as heavy water. After a few hours, the deuterium mixes evenly with the water in the body. Saliva or urine samples are collected to determine deuterium concentration. This allows scientists to calculate the total amount of water present in the body. From there, they can estimate the fat-free mass and the fat mass. Total energy expenditure. A person drinks a specific amount of doubly labeled water, containing both deuterium and oxygen-18. This mixes with the water in the body and is later excreted in the form of urine, sweat and breath. Urine samples are collected over a period of 2 weeks and analysed in a laboratory. The difference in the rates at which deuterium and oxygen-18 leave the body is a measure of the rate of carbon dioxide production, from which energy expenditure is calculated. Through an IAEA-supported project, Chile used both the deuterium dilution and doubly labeled water techniques to measure body composition and energy expenditure in children attending daycare centers. Results showed that the children were generally physically inactive and consumed, on average, 10% more energy from food and drinks per day than recommended. In response, daycare centers implemented a curriculum on regular physical activity and healthy eating. The IAEA provided support through continuous evaluation of the impact of the program. The new curriculum was subsequently adopted by the Chilean national authorities. This contributed to a decrease in obesity rates from 10.7% in 2001 to 8.4% in 2009 among children attending daycare centers. In this project, deuterium dilution and doubly labelled water techniques provided important data that helped inform childhood obesity prevention programs. These isotope techniques continue to be used in other countries to design and assess the impact of interventions to combat all forms of malnutrition and to monitor achievement of the UN's global nutrition targets. To learn more about how the IAEA supports the use of isotopes for better nutrition, please visit the Human Health Campus.